I'm Kathleen DeBroda.
And we're here to present Georgia Tech's work with National Science Foundation in the Food, Energy, and Water Initiative towards a mechanistic model of an aquaponics greenhouse. I'm going to introduce the concept of infrastructure ecology, which is basically the viewpoint of cities as ecosystems. And viewing cities as networks of infrastructure, interconnected and exchanging flows of material and water and energy. It allows us to view these systems as systems of systems, which allows the reorganization and alteration of energy and resource flows in order to optimize the performance and the efficiency of these systems in order to mimic biological ecosystems. As a test case, in order to examine this concept of infrastructure ecology, especially right there at the intersection of food, energy, and water systems, we've chosen the example of urban farming and specifically aquaponics in controlled environment agriculture. This method of production allows year-round cultivation, extension of crop seasons, and cultivation of a variety of different types of crops, all independent of geographic location for the most part. Aquaponics is the combination of aquaculture and hydroponics, basically the simultaneous production of fish and vegetables in a controlled environment without the use of soil or the use of pesticides in order to spur productivity.
This is our mechanistic model of our aquaponics system, and it includes bound nitrogen, phosphorus, carbon, water, energy, and soluble nutrients, including nitrogen and phosphorus in the system. From what Tom was talking about, the major input is through here, where organic wastes are digested into algae, and that algae is then able to be fed to the fish in the form of dehydrated pellets. And the major takeaway from this is that the outcomes are fresh fish and fresh vegetables, whereas the rest of these other components are cycled throughout the system and not wasted. So the major approach we took to modeling these different components of our aquaponic greenhouse, for nutrients, we based it on monokinetics for the uptake of nutrients by the plants. It's photosynthesis driven at the end of the day, so it's limited by the total photosynthetic leaf area and the genetics of the plant itself. The most difficult part so far has been modeling the dynamic interactions between the fish uptake rate of nutrients, their rate of waste, the rate of plant uptake of those nutrients, and the related wastewater treatment processes. For the water balance, we have to model the interaction between the evaporation from exposed water bodies in the system, and harvest of water containing biomass. And the energy is highly dependent on the system itself, the size, the equipment that you need, the climate that you're working in, and there are multiple different inputs for that energy. So there's grid energy, solar energy, there's combined cooling, heat, and power, or even waste energy, which can all be tied back into our algae digesters and other parts of the system. So the overall takeaways from what our model is trying to accomplish is we want to maximize the productivity of this aquaponics system to get the most fresh food possible from existing waste streams in an urban system. So we want to produce a functional model that, importantly, is deeper than just a black box understanding of inputs versus outputs of the system. We want to understand the system dynamics, the system demand for nutrients, for water, for energy, and for the potential supplies in a city to get as efficient as possible of a system in place.